The last part of the equilibrium chapter is just a couple of applications of Le Chatelier's principle, basically. And the first of them is carbon monoxide poisoning. Now, as you no doubt know, carbon monoxide is a toxic gas which can be fatal at low concentrations. And this is because it binds very tightly to haemoglobin and prevents haemoglobin from carrying carbon dioxide and oxygen through the body. Now, this can be thought of as a couple of equilibriums. First of all, there is the reaction between haemoglobin and carbon monoxide to form carboxyhaemoglobin, and that is the reaction that is favoured. That has got a very large equilibrium constant, much larger than the equilibrium constant between haemoglobin and oxygen. So therefore, if you've got a mixture of oxygen and carbon monoxide, it's the first reaction that's going to be favoured. So we can combine those two. We've got haemoglobin in both of them, so we can produce a combined equation. And in this case, the carboxyhaemoglobin side is favoured, so we've got a very small equilibrium constant. So it doesn't take a very low concentration of carbon monoxide. It's going to send this reaction strongly to the left. You're not going to have any of the oxyhemoglobin. You're not going to be able to carry oxygen in your blood. You're going to be in trouble. So what happens? One treatment for carbon monoxide poisoning, of course, is getting the patient to breathe in a very high concentration of oxygen. So if you increase the concentration of oxygen, it's going to push this reaction to the right. And that, of course, is the treatment for carbon monoxide poisoning. Give them pure oxygen. So basically, put that information into the answers to these questions. Now, as I've said a couple of times through this, a very important part of the physical chemistry we're doing now is its application in industrial chemistry, maximising rates and yield. So you get a lot of chemical, i.e. a high yield, and you get it quickly, i.e. a rapid rate. Both of those are very important. Sometimes it's a little bit easier said than done. So what have we got? If we want a rapid rate, what do? We have high pressure and concentration, high temperature. What else can we do for a rapid rate? Well, we can add a catalyst. We can have a high surface area if we're dealing with solids. What factors will produce a high yield? What do we do to pressure and concentration to get a high yield? Well, it depends on the number of particles. If the right-hand side has got more particles, then it's a low pressure. If the right-hand side has got fewer particles, it's going to be a high pressure. Temperature, what do we do with temperature to get a high yield? Again, it depends on whether it's endothermic or exothermic. So, if it's an exothermic reaction, a low temperature will favour the yield. If it's an endothermic reaction, a high temperature will send it to the right to get more yield. What other factors? Excess reactants, removing products. So how does that play into a particular chemical? Well, let's have a look at catalytic oxidation of SO2. Very important. We go through an enormous amount of sulfuric acid in this society, so we need to make lots and lots of it, and this is the central reaction. So, what have we got? We've got an equilibrium between SO2 and SO3. It's a strongly exothermic reaction. 3 particles on the left, 2 on the right. So if we want, well, what should we do with temperature? If we want a rapid rate, what temperature gives us a rapid rate? Always high temperature. What about a high equilibrium yield? Well, it's an exothermic reaction, so that means we need to reduce the temperature to send it to the right. So we have a conflict between the temperature requirements for a rapid rate and the temperature requirement for a high yield. What do we do to resolve this conflict? Well, using a catalyst enables us to get a more rapid rate at a temperature, lower temperature, which still gives us a decent yield. What about for pressure? Rapid rate, always high pressure gives you a rapid rate. What about equilibrium yield? What sort of pressure is going to give us a good yield in this case? Well, we've got fewer particles on the right, so if we increase the pressure, it's going to want to go to the right. So, in theory, high pressure favours both. However, when you're talking about these massive industrial systems with gas phase reactions, high pressure is really challenging. So they actually do it at atmospheric pressure because the increased yield by using high pressure just isn't justified economically. Other considerations, catalyst. What are we going to do to get the catalyst working better? Well, high surface area, multiple beds, just prolong the period of time that it's in contact with the catalyst. We're going to use excess oxygen to drive the reaction in the forward direction. Air is cheap, so that gives us a better conversion of SO2 to SO3. And on to the questions. So submit your answers to these questions and I'll send you the solutions. And that's the end of Chapter 8. Time to do the review questions and submit those. Thank you.